everybody, it's Miss Phoebus, and I'm back with our last lesson, lesson 67. It's on correlation versus causation. Correlation is a numerical measure that can show whether and how strongly pairs of variables are related. So, for example, we look at height and weight. Are they related to each other? Well, taller people may tend to be heavier than shorter people. How well are those related? Does that necessarily have to be the case? That's the question. But correlation is how are variable pairs related. Causation is a relationship between two events where one event is affected or caused by the other. In statistics, when we look at the value of one event or variable as it increases or decreases as a result of the other event. And that we say that there is a causation there. All right, so your skill for this lesson is I can differentiate between correlation and causation and looking at the differences between the two kind of thing. And then our state standard is the same thing, distinguish between correlation and causation. So we're on page 315 in the notes. You'll have to backtrack just a little bit. And when you get there, you're not going to see this, but this is what I usually like to start with. And this is back in 2015. The headline is that the Oklahoma senator wants to ban hoodies. And the reason why he wants to ban hoodies is that it has been found that hoodies are linked to crime. So more people are being arrested and things like that, doing crimes, criminal activity, and when they are doing that, they are wearing hoodies. So therefore, if we ban hoodies, we'll lower crime, right? Because these things are happening together. That's that correlation, right? Well, we have people committing crimes. These people are also wearing hoodies. Therefore, the hoodies are encouraging them to commit the crime. That's the correlation part. Trying to blend it over into a causation part, right? So because these two things are happening and they're related to each other, one causes the other. And so if you think about that, that doesn't truly make sense. And if you also think a little bit deeper about it, well, I'm pretty sure that those people were probably also wearing pants, maybe even socks and shoes, perhaps even underwear at the time of those crimes as well. So why aren't we banning those? So that argument kind of becomes null and void, and we end up having people say, you know, this doesn't make sense, and getting very, very upset about it when, you know, the person that originally started the problem was thinking about, well, this causes this, then we'll just get rid of A, and then B won't happen anymore. Whereas, yeah, they're related to each other, you know. People may be, it's an article of clothing. People may like them because they're comfy or they have like a big pocket or something like that, you know, but does that necessarily cause the crime? All right, so there is a video, and I can show it here, but you won't be able to hear it. It's a Simpsons clip, but I want you to go and watch it. But without proper interpretation, causation should not be assumed or even implied. So in the Simpsons clip, let me just give you a rundown of that. There is a bear that makes its way into Springfield and starts going through the garbage cans. So they create this bear patrol. And so because they have this bear patrol now, then it's keeping the bears away. And so that's that whole correlation, right? We're bringing in the bear patrol. It's now here and there are no bears. So that's the correlation. And so that implies the causation of the bear patrol is stopping the bears. And Lisa is hearing Homer talk about this, and she's like, Dad, that's not even, no. She's like, that's like arguing that this rock is keeping tigers away. but there are no tigers around, you know. So the thing is just because it appears two things are in a relationship with each other, right? There are no tigers and there is a rock present, doesn't necessarily that one is causing the other thing to happen or to not happen. It is a Simpson clip. You can watch that and kind of see. I like The Simpsons a lot, and so kind of see they work a little bit of math in there as well. All right, so correlation does not imply causation, and you will hear that, especially when you get into upper level mathematics and statistics and people getting into arguments about things. So what does this even mean? What this means is a causal relationship between two variables exists if the occurrence of the first causes the other. So we can say, yes, this causes this, but we have to make sure that it truly does cause it. A correlation between two variables does not imply causation. Just because two things are happening and they happen to seem to have a relationship does not mean that one thing causes the other thing to happen. If there is a causal relationship between two variables, they have to be correlated. So if something is saying, yes, this has an effect on this, then there should be a relationship there. So the thing is that they can be correlated and not be a causal relationship. One causes the other. But if they are in a causal relationship, they have to be correlated. They have to be related. So correlation does not imply causation, but causation does imply correlation. So what that means is sometimes I might have two variables, right? They look like they're related, but there's a third thing doing the causing. So that's a lurking variable. And a variable not included in the relationship that can affect the relationships of the other two variables, that's a lurking variable. So if I am thinking that here's X and here's Y and this causes this to happen, and it looks like they appear to be related, we can't necessarily say that X causes Y because there might be an outside influence, an outside variable making that change happen and maybe even affecting both of them. So I love these. These are my favorite. So the red that we see here in the graph, that's the letters in the winning word of the National Spelling Bee. And the black is the number of people killed by venomous spiders. If you look here, there's a percent correlation, 0.8. That's pretty strong positive correlation. And so that means that the numbers of the winning word of the spelling bee, the letters in the words, and the number of people killed by spiders, one causes the other, right? What do you think? Do you think the number of people killed by the spiders causes the spelling bee thing to happen, or the letters in the spelling bee cause the spider thing to happen? They don't. One doesn't cause the other thing to happen. They have what appears to be a pretty similar relationship, but there is no causation. One does not cause the other. All right, let's look at another one. You ready? The per capita consumption of chicken and total U.S. crude oil imports. So how much chicken we eat as a country and how much oil we bring in, they're correlated. Look, 0.8999. That's pretty good, right? Pretty strong. But guess what? They have nothing to do with each other. How much chicken we eat and how much oil we import, one doesn't cause the other to happen. People who drown after falling out of a boat, fishing boat, and marriage rates in Kentucky. Look, it's a 0.95, 95% correlation on a downward trend, right? Our marriage rates are going down, and our number of people who are drowning after falling out of fishing boats are going down. But they're correlated. Does one cause the other? No. Even though that number is really, really close, it is not causing the other one to happen. All right, per capita consumption of mozzarella cheese, and civil engineering doctorates awarded. All right, guys, we need more civil engineers, so I need you to eat more mozzarella cheese. Think you can do it? 0.9586. Wow, that's really, really strong positive. All right, divorce rate in Maine and the per capita consumption of margarine. Guys, we are eating less and less margarine, and look, our divorce rates are going down. No, they have no relationship there. But look at the correlation, 0.99. So when can we imply causation? So causation can be extremely hard to prove, as what you're trying to prove is 100% correlation, which rarely happens. Experiments, while not always able to be run, experiments are one of the more helpful tools to prove one variable causes the other. And some experiments, and I'm using air quotes that you can't see, some experiments we view every day. Like, we should expect, as we move into the next day, the sun should rise and set, things like that. Or as you grow older, you should grow taller, things like that. Those are kind of experiments, right? If something was to happen that, okay, we wake up the next morning and the sun never rises. There's a problem there, right? We should expect some of these things. Yes, one thing causes the other thing to happen. We move into the next day, we should expect the sun to rise, that kind of thing. So some of these things we can view as, yes, this is a daily occurrence, this is something that is expected to happen, that would be a causation. But if we're grabbing two different variables and saying, I don't know, they look like they're correlated, does that mean that they cause one another? Like back in the day when people didn't really know that smoking caused cancer, there were some thoughts that it did, but we couldn't necessarily say that smoking cigarettes cause cancer until we ran experiments and we looked at the habits of people that are smoking and what kind of effects in the long term did it have on the health of those people. Okay, so you can have the idea that, yeah, it appears that they're related to each other. That's the correlation part, right? But until we have more data and more reliable data that shows that, yes, every single time we're looking at this and it seems to be one thing is causing the other, and you're looking at that via an experiment kind of idea, that's going to be more when you can do the causation part. What's a direct link? It's a connection between two variables that can be explained by a third variable. This can be a lurking variable, or sometimes it's called a confounding variable. So there's another video here, and I wish you could see. It shows the picture. It's like an ice cream cone chasing a guy with a knife in a house on fire. It's another one. It's called How Ice Cream Kills. But basically, it shows the number of ice cream sales going up and the number of deaths by stabbing maybe or fires or something like that also going up. And so there is a correlation and there is a direct link between them, but ice cream sales aren't causing people getting murdered. It's something else. It's another variable. So this is another video that I want you to go and watch. So you watch the Simpsons clip, you watch the How Ice Cream Kills clip, and I actually like this one. I like watching people draw things. I think that's really cool. And then there's another one. This does not equal that. So you can watch this. I think this is another one. And it very closely looks at some of these things again. So these are some short clips that I want you to go back and I want you to look at and see if you can, I don't know, get the idea of correlation and causation, not necessarily having to be connected, but are, going to end up sometimes leading to a causation, but you're going to have to work really hard to prove that it's a causation relationship. So there are some out there. And this is one of my comic strips that I like. Correlation is not causation. I used to think correlation implied causation, which we know we shouldn't, right? And then I took a statistics class. Now I don't. So now he knows that correlation does not imply causation. And it sounds like the class helped. Well, that would mean that his getting help on understanding what correlation versus causation meant, it might be correlated. Did it cause him to understand it better? It goes back to another, did the class cause you to understand that? So do you get the joke? All right, so I really like this lesson. It is full of, in the homework, it's full of some bad graphs. Just because the graph looks good doesn't necessarily mean that it's a good graph. Look at the variables that are being used. Look at how the data is trending. I think I have one on there, something about the number of pirates and global average temperature. So play around with that idea of how would those two variables be linked. But there are going to be things that, the variables can be, yes, this and this are correlated. This causes this to happen. But if you can't sit down and think about, okay, I could build an experiment to show blah, 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 then, I mean, if I wanted to say hair length and grades were related to each other, that the length of your hair causes your grade to be a certain average, I would have to run an experiment to prove to everybody else in the world that it was a real thing. You should not believe that hair length causes your grades to be something else. Even though maybe my data I can show and handpick, even I can show and handpick values that are going to be very well correlated and create a very strong argument in order for me to actually be able to sit down and say, yes, this causes this, I'm going to have to support myself with a lot more evidence. Okay. And so that's really what you need to take from this, because you've got to think about the media is always trying to say, well, this and this are related, so don't do this, or this and this are related, so you should really do this. You need to kind of not necessarily not believe that, but you might need to think about it and say, well, where did they get this information? Was this done based off of an experiment? I mean, for years and years, back in the 80s, eggs were bad for you. And then later on, eggs were good for you. And then eggs were bad for you again. And it's like, make up your mind. And they are doing experiments when, scientists are doing experiments when they're putting out that information. And so even with that, eating eggs causes your cholesterol to go up. Eating eggs, it causes your cholesterol to go down. It's like, which experiment are you going to believe after, some point in time? So really be very cautious when you are receiving information, especially when they say studies say blah, 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 blah. Be very careful and say, well, what kind of study was it? How many people did they do the study on? Those kinds of things before you actually just go, oh, okay. You are a consumer of information, especially as you become older, and you need to make sure that information is good information, because sometimes that ends up, leading to decisions that you make on your part or on the behalf of, your family or things like that. So that's the only thing that I really wanted to kind of put out there, that just because two things happen to be, related to each other does not necessarily mean that one causes the other. And if you think that it does, but it doesn't make sense, or somebody's telling you that they are related and one causes the other, but it doesn't make sense, just remember that correlation does not mean causation. It just doesn't. And so it's one of those things where you kind of have to think outside the box and not just go with what other people are always telling you. Alright guys, that's the last lesson. Don't forget to watch those other videos. I think they're pretty cute and educational. Um, I appreciate this semester. Those of you that worked hard for me, I really, really do. And I hope that you have a great next semester and a great next year. And if you ever need help or anything, you are welcome to continuing to email me. And you want to drop by if we come back from school and say hi, or you need tutoring or something like that, you are always welcome to drop in, and I will do my best. I'm not the greatest at geometry, but I can try. All right, I'll see you guys later. Bye.